when I heard about the honor of getting the gold medal, I thought there must be a mistake. Because many of the gold medal winners are my professional heroes. And by definition, one cannot rank with his own heroes. So what I can do, however, is accept this honor as a representative of Schlaich, Bergermann und Partner, our office that my father Jörg Schlaich, you have heard, he got the gold medal 25 years ago, and he has founded the office together with his partner Rudolf Bergermann. 10 years ago, the next generation took over, and I've been directing the office together with my 3 friends and partners, Knut Göppert, Andreas Keil, and Sven Plininger. And here they are. Well, if you count correctly, there's another Knut on the right side, so now we are 5 since the beginning of the year. These are the directors, the partners of Schlaich, Bergermann und Partner. And the little black dots here are our offices. So there's the main office still in Stuttgart, and I'm presently in Berlin. I'll tell you why later. There's an office in Shanghai, and the little orange dots are projects. So you see, we are active all over the world, and there's also, there should be a little dot in Singapore also. Anyways, my talk is about a German word, Gesamtkunstwerk. My talk will be about goals, about ideals, about what we engineers should strive for, about the question, what is good engineering? And naturally, this will be my personal views, and you must decide if you want to subscribe to them. The goal can be illustrated with this word, this German word, that has made its way into the English language as a term in aesthetics. The dictionary defines Gesamtkunstwerk as an ideal or total work of art that makes use of all or many art forms or strives to do so. My view is that structural engineers should strive for such an ideal in our work. By following principles of good building, we can provide quality structures that by themselves or as part of a building and together with other disciplines contribute to the culture of building and to the quality of all our lives. We can engineer quality structures that are or form part of the Gesamtkunstwerk. So this is the idea. Naturally, these ideas come from somewhere, so I want to start with influences. What has influenced me? I'd like to talk about the question of what is good building, and I'll talk a little bit about the term elegance also, and then there's 2 more chapters, so to say, education and research. So this is what you're about to hear. I started studying in Switzerland, and I was very happy when I found this little map, and each of the green dots that you see here is a bridge by Robert Maillard. So since the ETH in Zurich is more or less centrally located, I could on the weekends go visit bridges. And this one you all know, that's the most famous one. And it not only shows well-dimensioned sections, it shows elegance, it shows integration into the surrounding, it shows good design stemming from the context, it shows flow of forces, it shows beauty, it shows that someone has understood a material and used it in a proper way. All that can be learned from this bridge and the bridges of Robert Maillard. And there's other good, well-known engineers I could study with, Christian Menn, and that's my favorite of his bridges, the Simplon Bridge, the Ganter Bridge. And it looks a bit like a sculpture. It's not easy to understand from the start, but if you take the bridge, the Ganter Bridge, and zoom in, what you see at the top right, and then turn it upside down, what works in tension, if you turn it upside down, works in compression, and then go left, all of a sudden you see that it is a bit like an inverted raked frame, like Robert Maillard's Saginaw Tobel Bridge. There is a striking similarity. Consciously or unconsciously, there is a history that can be seen in these bridges. Heinz Isler, the shell builder, showed us slides at the university. This is design by experiment, by model. He took the wet cloth in the cold Swiss winter, hung them out in the garden. When they were frozen and hard the next morning, he just turned them upside down, and from the hanging shape, form-found shape, he developed his beautiful shell structures. One of them you see here, isn't it a beauty? And it's derived from hanging shapes, lightweight structures that at least impressed me very much for many reasons. After that, after 8 years in Zurich, I went to Spain and got to know Spanish engineering, and I found out that decades earlier in Spain, a lot of shells had been built already, different from the German shells. There was Stischinger in Germany who in the 20s developed a theory of cylindrical shells, and the Germans built anything they could calculate. Once they had understood how shells were calculated, they built lots of cylindrical shells, but nothing else, while the Spanish, they built even what they could not calculate. And I think these shapes were much more interesting, to be honest. So this is the roof of the Hippodromo in Madrid, and it was designed by model. This was a one-to-one model that Eduardo Torroja built in order to make sure that this structure that they could not calculate really at the time would work. And it also taught me about economizing, because the story is that once they had made sure that the model would work, they hammered the concrete away and reused the reinforcement later for the real building. That's another engineering virtue, so to say. This gentleman, Felix Candela, did most of his work in Mexico, but he is Spanish. He studied architecture in Spain. He almost went to Germany to study shells with Stischinger, but then the Civil War came and he had to go to Mexico and build a lot of hyperbolic paraboloids with this great idea that you can do this with straight generator lines, which makes scaffolding much easier. Another lesson that can be learned from this impressive gold medal winner from Spain originally. Well, and last not least, definitely not least, my father, Jörg Schlaich. He was the project manager, the engineer in charge of the roof of the Olympic Stadium in Munich, the games, 72 games. And this structure still impresses today. If you go there, it's still something really special. And I think it also left a good impression about Germany. Germany, after the war, after all the heavy Nazi stuff, showed lightness, showed openness. I think it was it's a landmark structure for Germany, for post-war Germany, and it's a lightweight structure. From my father, I learned the principles of lightweight structures, and here they are, the secrets, so to say. There are 5. I found 5, and one is small spans. The smaller the spans are, the lighter your structure gets. It's something that we sometimes forget with our record buildings, record spans. We should avoid bending. The more we can work in tension and compression, the lighter our structures get, because bending is expensive. We should use long breaking length. High strength, low weight materials are very helpful, especially because they can be pre-tensioned, and pre-tension helps reducing deformations and makes our structure lighter. And finally comes the high art of engineering, double curvature. Small spans. If the spans are small, then even stone plates can become slender. And if you have to work with bending, at least we can shape our structure so that they look a bit lighter. This is a 2-span continuous girder, and if you shape the bridge according to the bending moment distribution due to distributed loads, then a pedestrian bridge can look like that. Very lightweight, very economic also. And then when the bridges get bigger, then it's good to avoid bending. For 500 meter span, then a truss, and the cable stayed bridge is nothing but a truss, works nice. Tinkau Bridge, Ian Firth and I, we have been knowing, we got to know each other there on this project that cost me 5 years of my life, and I do not regret a single one. It was really very special times, learning a lot. And then comes pretensioning, high strength materials, double curvature, all that you see in this little, you see this collected on this little roof, which is in Wolfsburg. Wolfsburg is in Germany, where Volkswagen builds their car, and they have a distribution center, so you can pick up your new Volkswagen. And what people then do, they drive away, and after 200 meters, they stop, they open the trunk, they look at the engine. So there was cars scattered all over Wolfsburg with new owners testing their cars, and this is why they decided to build a special parking place for the new car owners so that they can in peace open their car and look at it. And they needed a roof because it's raining quite frequently there. And so this is how we could design this roof together with craft architects. Double curvature, high strength materials, stiffness through pretensioning, and double curvature. Here's the project at night. Just like a leaf, and again, there's historic roots. You all know the Raleigh Arena in the United States. This is where this comes from, but it's not supported along its edges. You know, it's freestanding, all balanced. Now, I like lightweight structures, and I think lightweight structures are good structures, but what really is good structure, and even further, what is good building? I think we all agree that we need good buildings. Good buildings lead to quality of life, they enhance quality of life. Good buildings need to be, however, I think, completely good. A building needs to be of holistic quality, a Gesamtkunstwerk. It cannot only be good in some aspects. It's not enough to just fulfill the codes, for example. So if you start designing, I think first of all, design work needs to be a conscious act. We cannot just start somehow by opening the codes. We have to really think. And secondly, I think it's the context, like we have seen it with Salgina-Tobel Bridge. We have to study the boundary conditions. They can be topographical, they can be financial, it can be the chemistry of the design team, but there is always a local context that helps us to go towards a good design. Question is this enough? I consulted books, and here are 4 of them that somehow again influenced me. The classic Vitruvius, the Roman architect. And what is interesting is he comes up with 3 principles for good design, and all the others also. It looks like there's always a trias, a trinity, where 3 principles fuse into one holistically good thing. So I think the first 3 are easy to understand. Firmitas, our buildings have to stand up. Utilitas, they have to be useful, and they better be beautiful, Venustas. My father, that's the second book on lightweight structures. When he talks about lightweight structures, he also has 3 principles. He says lightweight structures are or should be ecological, in the sense that they minimize the use of materials, in the sense that they're easy to demount and they're easy to recycle. They're social because they create work for well-trained engineers and well-trained workers. And finally, they contribute to the culture of building. They please because of their lightness and their transparency, and this is where the cultural issue is. There's a German architect, Volkwin Mark, from GMP Architects. We have been working with them many times, and especially because they are compatible with engineers. They understand the engineer's language, and I think we also understand theirs. And he also uses 3 words. He looks at building as a coin where you have technology on one side and art on the other side. And he believes that truth appears when engineers and architects work well together, when the 2 sides of this coin fuse. He believes that then comes goodness, when true structure have a good influence on society, when they're helpful to society, And finally, he says, beauty appears when truth and goodness really act together. And I guess now comes a book that many of you have read. It really has influenced me a lot, The Tower and the Bridge by David Billington. I read this book and learned about the British engineers, Telford, Brunel, Stevenson. I read about the engineers who shaped modern American bridge design, Röblin, Ammann, and all these engineers that came initially from Europe. But Billington does not see the coin that Mike has seen. Billington, in a way, is a fundamentalist. He says the art of engineering, and he has coined this term, the art of the engineering. The art of engineering is independent and parallel to architecture. So he is very straightforward and strict. He does not. He's separating the engineer's work from architects. He says there's efficiency, economy, and elegance. And contrary to the scientists who discover, we engineers invent. And the inventions of the engineer, the tower and the bridge, they are elegant when minimized use of material, economy, and minimized cost. Efficiency and minimized cost, economy are the result of a conscious aesthetic decision. Then elegance appears. So I think I always wanted to make a word cloud. Here it is. We have seen one this morning already. And I do this cloud purposely because I do not think that we have to be dogmatic. I don't think that there's only 3 principles. I think we cannot freely choose the principle, but there's freedom. We don't have to be dogmatic. We can choose the ones that we feel best with. Perhaps you have seen that, we have noticed that sustainability has not appeared in these principles. I think it's inherent in many of those anyway, so it doesn't have to appear here individually. I think it's there anyways. It should be a conscious process, then we can choose. And what is interesting is the little word on the bottom left, elegance, that the engineer Billington has used as the only one in these 4 books. And elegance has made me think a lot. What is elegance? Is elegance really an ingredient for good building? So perhaps you want to close your eyes, or the ones who sleep can keep their eyes closed, and think for a moment of what comes to your mind when someone uses the term elegance. What is elegance? What's the picture that comes to your mind? Not only a structure. What is elegance for you? Many people would say it's the ballet dancer that we have heard about earlier, but it's a very subjective issue. Many people, or everyone has his own picture. Elegance has got to do with beauty, I think, but it's beauty plus. It's beauty plus movement, it's beauty plus lightness, beauty plus transparency. All this comes together when we think about elegance. There was a YAPSE conference in spring in Nara on elegant structures. And there is a lot of elegance in Japan to be seen. It's sometimes elegance plus purism, plus reduced forms, like this beautiful tea house with the window that looks like a painting in the background. I find this most elegant, and this is the Emperor's Palace in Kyoto, not like the German palace's Baroque gold ornament. It's very reduced shapes that I think have got to do with elegance also. There was the German architect Ono Taut who visited these palaces, and he wrote books about it and published them in Germany. And the Bauhaus movement, I'm sure, is influenced was influenced by this book. This is Mies van der Rohe's Farnsworth House close to Chicago. I think it's elegant. It's elegant, and I think, comes close to the most important definition of elegance, because elegance can be defined as effortless beauty. Beauty plus, but here effortless beauty, that means something is elegant if you feel that a lot of effort was put into it. It was not easy to achieve that. It looks natural, but it was not at all easy, but you do not see it anymore. So this is effortless. I think that is an important characteristic of elegance. So I think elegance appears when the complex fusion of these principles of good building to holistic quality works, so that a Gesamtkunstwerk appears, that the Gesamtkunstwerk appears effortless. Elegance makes difficult matters appear easy. Leading a good life is not easy, and it's difficult, and we want to live it in elegance. And this is, I think, why we need elegant buildings, why we need elegant structures, so that we can perhaps say we want good buildings because they lead to a good life. We want elegant structures because if we live in elegant structures, if we are surrounded by elegant structures, perhaps we can live an elegant life. Elegance you can see here, but it's not only the final product. Elegance can also be found in the way we calculate, in the way we construct, in the way we erect our buildings. Can be elegant structures, elegant structural approaches. And here's an example that my father drew in the early 90s. It's about integral bridges. I think integral bridges are quite an elegant approach to bridge design. At the top, you see a typical German railway bridge, the standard design that was done all over Germany, anywhere, no matter if there was a river or no. Every 40 meters there was a pier, and then they put the 40-meter box girders, post-tension box girders. And sometimes this makes sense, but not always. And if possible, there is an alternative shown at the bottom where it's a continuous concrete beam, small spans, and all monolithically connected. Then the bridge becomes much more slender and much more robust, even more economic. And the German reunification gave the possibility to build a few of those bridges. The new railway lines had to be built to connect east and west, and that is the Gänsebachtal bridge close to Leipzig. Well, it's not the bridge yet. It's during construction apparently, but you can see the slender columns and you see the reinforcement waiting up there to be connected to the deck. So there's no bearings, no joints in this bridge for a long time. This is the finished bridge, where actually it's 110-meter segments, but all these 110-meter segments are monolithically connected. You can also see the stiffer elements. This is for the braking forces in the longitudinal, but also in the transverse direction. Very slender bridge because of the idea of integral design. Here's the next example, Untitled Bridge, again close to the city of Leipzig. This is 600-meter segments with a central arch that again works for the braking loads. Again, at the top, you can see that the arch and the deck is monolithically connected, and this is how it goes all along the bridge. And here the finished integral solution. So I think integral bridges have a very bright future, so to say. I want to show you a bit more of our work. And it has got to do, I found, a lot with principles. Simple principles, simple ideas. The tennis racket, the salad sieve, the bicycle wheel, and just a little curved girder. And I'll give you some examples to show you what I mean with that. So if you look at the tennis racket, it works because it's highly tensioned. You have orthogonal or cables only in one direction, but you have highly straight, highly tensioned cables, and they provide you with the possibility to build very stiff walls. Here's an example. That is the new airport in Malaga. Well, it's not so new, 5 years ago. And this glass facade is only connected, the glass panels are only connected to highly tensioned cables. In this case, it's actually only vertical cables, but these cables get a lot of additional stiffness due to the tensioning, and it's not only the overall concept, since I want to emphasize the idea of the Gesamtkunstwerk, I think we have to also go all the way down to the details and treat the details with care and love. And this is the connection of the windows to the steel cables, or to, here you see little steel rods in this case, that I think is also a very important task of us engineers. The salad sieve. Salad sieve can be laid flat on the kitchen table if you cut it open with a pair of scissors. If you cut through here, you'll find out this net will go flat on the table, and you can deform it because there's a possibility of rotation in the joints, and all the squares that you have are of equal length. So you can build such roofs, such structures with all equal elements as long as you allow rotation in the joints. And the very first example was the Museum of the History of Hamburg in Germany in late 80s. It's a cylindrical shell, and then here comes the salad sieve where the two cylinders connect. This idea was applied for the first time. And again, the details. A cylindrical shell needs to be stiffened, and it can be stiffened by tension cables. And this is, I think, the joy of engineering, where you can detail such connections, where you show the flow of the forces, where you somehow try to produce something beautiful. Well, ever since then, dozens of glass roofs, glass shells like that were designed in our office. I do not want to go into the details. It's just the one here I want to show, Bugis Junction here in Singapore. That's the only project that I found that our office has done in Singapore. And it follows this idea of the salad sieve, the all equal elements, steel elements, the steel grid, the stiff shell steel grid. Another concept, another idea that I want to elaborate a little bit more on is the curved girder. On the left side is a straight deck, a plate, and straight decks always need pairs of supports. If you take one row of supports away, the entire thing will fall over. There will be too much of torsion. But if you have a circular, if you have a curved girder, then you can support it only with one row of columns, as you can see here in the center, or you can move the columns also to the inner edge. You can support these curved girders by columns in compression, or you can hang it by cables. Then it would look like that. Again, this is our first curved pedestrian bridge in Kelheim in the south of Germany. The curved girder supported by hangers only on one side, and the torsional moment, so to say, that appears here can be converted by the girder into bending, flexural bending, so it can stand up without any trouble. And also this system, this idea we have used many times. This is a footbridge in the north of Germany, the island of Rügen in the Baltic Sea. Actually, that's again a product of reunification. The port down here was for the Westerners, for the West Germans, because they could go through a highway to here and then take a ferry to the Scandinavian countries, crossing the Baltic Sea, while the East Germans were cut off through the wall and were standing up there in their village. And after reunification, the village was then connected by this bridge to the port. The idea here is that little cantilevers prop out of the deck, and the axis of the cable thus can go right through the center of gravity of the deck, and this way torsion is avoided altogether for distributed loads. And this is how the bridge then looks. You see the individual cantilevers that have to carry bending by themselves, but the deck can be very slender. It's a 120-meter deck and only 70 centimeter structural height. So also this type of, we have played a lot with these curved girders because they're really fun and they're not so expensive. So here's another example, a monolithic connection, again, integral bridge, because these curved girders, they can breathe through due to temperature. There's no big strains. So you can make integral bridges here also. Again, the idea of turning things upside down. If you have a straight load, the cable will be in a vertical plane if you build such a suspension bridge. If you have a straight deck, you can just invert the hanging cable, and you get the arch in compression only. The same you can do for a curved deck. If you have a curved deck, the cable automatically will be a 3D shape. It will be a 3D curve in tension, and if you put it upside down, then you would get the ideal form in compression. And we have toyed with this idea. This is a bridge that we have done the detailed design for this bridge in Belfast, but then the financial crisis hit hard, and so this is why it's not built so far. But this follows just the idea what I just said. It's a curved deck supported only on one side, and then it's this arch that is basically the inverted catenary. It works in compression only for distributed loads, would be 120 meters and only 1 meter diameter for the tube. Well, final concept here, quickly, the spokes wheel. It only works due to tensioning, highly tensioned spokes make this a very stable structure, an outer compression ring, an inner tension ring, and the first large spokes wheel that we have done in our office is this roof in Stuttgart. Works like a spokes wheel, outer compression ring, inner tension ring, and then the spokes, radial cables connected to, tension the two, so that it becomes a very lightweight but very stable structure. And also from this idea, by now we have designed more than 24 or 30 stadium roofs like that. I just want to show you quickly one that I specifically like. Was directed by my partner Knut Göppert. It's the National Stadium in Warsaw, in Poland. That looks interesting from the outside as an overall concept. It's like a basket, a woven basket, painted in the colors of Poland. And from the inside, it looks, you can detect that it is, again, a spokes wheel. There is an outer compression ring, there is an inner tension ring, but also there's a further component. There's a movable roof, because there's another basket here. This basket can be lowered, and then 12,000 square meter of membrane are pulled out and cover the entire inside of the roof. Now all this is hanging on a large needle, 70 meters high, I think about 150 tons, supported. This supports the membrane later. There's 4 sets of cables at the bottom and more than 40 cables at the top. And here we go again to the detail. So if you go close to the bottom part, we are here, then this becomes a nice big detail of cast steel. And if you look at this one here, then you see the wheel here. And again, this is what I like so much, to detail the flow of forces so that it really works. And at least if you look at it from a distance, it looks even small and lightweight. This is how this column was erected. There was a hole in the ground, then all the radial cables were pulled, and this is how the needle then was lifted up. Here you see our details again, the cast steel element at the bottom and the welded element at the top. Well, all this you can learn, but it needs to be taught. And this is why I want to now venture into the field of education and a little bit of research also. I became professor at the Technische Universität in Berlin about 10 years ago. And this is our lab. You'll see it in a second from inside. It's the old AEG factory. AEG means Allgemeine Elektrizitätsgesellschaft, and that is basically General Electric. So it's the German General Electric. They had huge factories until they disappeared in the mid-80s. And this is the inside of our lab, 180 meters, where we can toy around, where we can do our experiments. And these are our students. And the first thing I tell them is that they chose a good profession. They chose a good profession because the individual can still visibly contribute to building, to society. You get your own building in the end. And they have chosen a profession where, like in very few other professions, you can combine creativity and theoretical scientific knowledge and creativity. While this, I think we all agree, or most agree, in the practical world, in the universities, this is still not so common. In many universities, only theory, only codes are taught, and I think that is a bit critical. Once a year we open our doors. This is the big lab, also to children, and we have competitions. Here it was the competition to build a tower with spaghetti. They had these welding machines, and they could weld spaghettis to a tower. And these are two of the results. I think that looks a bit like the Bank of China in Hong Kong. I think that a father must have been involved. And this looks like the alien has made it. So, but this is children's creativity, and I think this we have to maintain. And if we teach well at the university, then we can do structures like that. Another steel shell structure, architect Frank Gehry. And as I said, it should be a conscious process. We have to make our students aware that this can all be learned, that a good bridge can be integrated in the context, in the local context, as you see here, or it can make a statement, but it needs to be a conscious process. Otherwise, it looks like that. This is just fulfilling the codes, and this is not a contribution to the culture of building. And this, I think, and we have a big responsibility. Our structures last for 100 years, and they tend to be big. So we have to be careful with what we do. And I think this needs to be taught. And therefore we teach conceptual and structural design at the university. We believe in the basics, they're absolutely necessary, but on top of that, I think there can be more. And this is how I define conceptual and structural design. The first step, top left, is conceiving a structure, the famous sketch on the napkin. Come up with an idea. And this is an educated sketch, so to say. You have to know the basics, but then you can do such sketches. Then comes a very difficult, I think, step of abstraction to convert this sketch into a model, into a finite element model, or whatever it is, to apply the loads, to get the forces. And from these forces, then, that's modeling, you do the dimensioning, you dimension the sections, you dimension the cables. That is done at many universities, these two steps. But then comes the detailing. Our structures fail in the nodes. You have to connect the cable to the deck. How do you detail a nice steel node? I think that needs to be taught at the university also. If we do not teach it there, it might be too late sometimes. And in order not to get lost, we have also made a little order of structures. I don't know if you can read it. Basically, the most simple components is the arch in compression, the cable in tension, and the beam in bending. Basically, everything can be derived from that. If you go to the first circle, is the linear structures, the bridges are either arches in compression or hanging cables. You see there's a mirror axis. Basically, all structures can be converted from compression to tension. If you add many bridges together, then you get a plate, from the beam to the plate, from the arch to the vault, and from the suspension bridge to the hanging roof. And you can even turn it, and then you end up in the world of double curved structures, in the world of shells. I mean, there is some structures that do not fit completely into this order, but that doesn't matter. There's a lot that can be explained with this, and that helps the students to somehow get orientation. We did an interview with our first year students, 18-year-old students, and we asked them who their favorite engineer was. And the maximum we heard was Foster. Isn't it? And they said, no. And so this is why we started teaching a class now, which is Introduction to Structures, where we go through history from the, actually it's earlier than 500. We start with the Greek temples and the Roman arches. We go through history and we look at the evolution of structures. We follow Torroja's raison ser, the logic of form. We go through the evolution of materials, because the history of building is the history of materials. iron, steel, concrete. So it's very interesting to see how then new structural types appeared, how Maya worked with concrete quite differently than anyone else. Our history is also history of analysis methods. The Bernoulli family and the differential equations changed everything. And finally, we showed them faces. We showed them faces, persons, and buildings all through history. And after this first class, I think they all have the chance to have a favorite engineer. We go for walks. Nothing special, but we go for walks and look at buildings to understand them, to study the flow of forces, to find out, can they be studied, or is everything hidden behind the facade? We teach for all materials, or independent of materials, however you call it. In German, we call it werkstoffübergreifend. So we say dimensioning of sections. This is our book for dimensioning of sections. It's dimensioning of steel, concrete, membranes, there's cable, steels, timber, glass. It's all the same. In the beginning, it's all elastic. Only after a while, some materials crack, others go plastic. But we try to teach dimensioning independent of the material, and the same for bridges. Here is Switzerland. This is typical in Germany. We have a steel professor who teaches only steel bridges. We have a concrete professor and a timber professor. I don't know how it is in other countries, but this is an artificial boundary, an artificial wall between materials. And we try to teach bridges 1, 2, 3 independent of the material. Simple bridges, more complex bridges, but independent of the materials. This is how we try to do it. And all this leads to possibilities for research, but I think the main research point is the issue of sustainability. I'm sure we cannot hear this word anymore, but still it is important. And Germany has opted for the so-called Energiewende. The Germans have decided to exit from nuclear and fossil fuel energy. And this is very brave for such a big industrial country, I think. But it has boosted a lot of research activities, and that I think is wonderful. And a lot of these activities have got to do with either saving energy or producing renewable energy. So let me give you an example. This is, on the left side, the construction of 910 Lakeshore Drive, the famous Mies van der Rohe buildings in Chicago, very lightweight structures. During construction, you can see how sustainable they are in the sense that resources are minimized. If you look at the right side, this is one of the apartments today with single pane glass, with steel frames that go directly from the inside to the outside. So from the building's physics point of view, this is almost naive from today's point of view. And this is why, because we cannot only save resources, we also have to save energy. Such a very lightweight facade curtain wall could not be built in Germany, at least it could not be built anymore. Now, imagine for a moment that the energy we get would be almost free, renewable and clean. If that was the case again, then we could also again build buildings like that are very lightweight, that save, minimize the use of resources, and that can have single pane glasses and steel frames in the facade, because energy is no issue anymore. And I think this is why also we have to think a lot about renewable energies. In our office, we have been working on that for many years, on solar thermal power plants, not only for Europe. They can be built in Northern Africa and help the people there. They can create jobs in Northern Africa. They can resolve the energy problem there as well. So this is parabolic troughs, large mirrors that concentrate on tubes that are filled with oil, and the hot oil is then used to run conventional power plants. The advantage of these solar thermal power plants is that they produce heat, and heat can be stored much more easier than electricity. And our dream, again, invented by my father, and we continue this. We want to build it one day. I'm sure it will be built one day, and I'm sure it can resolve a lot of problems. Is the so-called solar updraft tower. It's a huge greenhouse with up to 7 kilometers diameter. The sun heats the air under the greenhouse. The hot air wants to go up somewhere, and it finds a chimney in the middle, 1,000 meter high. Wonderful engineering task, about 100 meters diameter. And this artificial wind then turns turbines, turns large wheels that produce electricity. So this is not built yet, but the power plant that I've shown you before, that's proven technology. There's no excuse anymore. We can build these right now anywhere in large quantities. But it will take some time. At this stage, energy, unfortunately, is not free, and it's not all renewable, and it's not clean, and therefore we have to save energy. And this is two examples of cheating. This is a Swiss chalet in the mountains, in the Rhone Valley. And if you look at the corner, it looks like massive timber beams, right? But if you look closely, you see here rock wool and very slender timber plates. At the bottom, it looks like solid rock, but then it's only like tiles, and behind it there's styrofoam, 20 centimeters. This is how we deal with insulation today, and we need a lot of energy to later save energy, and sometimes it doesn't even break even. And the Germans are a bit rougher. They just put the styrofoam there, concrete styrofoam, and then you have plastering, and it's a wild mix of different glues and materials. If you ever want to break down this house, you end up with a lot of toxic waste. And this is why we have tried to find out if we cannot make concrete the insulating material. So we have worked with what we call infra-lightweight concrete, very lightweight concrete with these clay bubbles as aggregates. We have made lots of experiments which were completely unsuccessful in the beginning. You see the clay bubbles up there and the cement down here, but in the end we could find mixes that work, and we are now building houses like that. This is the first one from 2007, all concrete house in the cold, minus 15-degree Berlin winter, only concrete, insulating concrete, very lightweight concrete, 50 centimeter walls, but no additional insulation. That can also work for hot countries where you want to keep the cool air inside because it's hot outside. So this is, it's no revolution, but it's an alternative to present insulation materials. Just make the concrete lightweight. Together with architects, Barco Leibinger, we have worked on large prefabricated elements. This is a prototype, a model of a house. So the pink elements would be infra-lightweight concrete elements. We've even won a competition. We took the money and built one large prototype. So you see, very lightweight. It can be carried with little cranes because this concrete is only 800 kilos per cubic meter. It's only a third of normal concrete. And we got the Holcim award for this. So at least we have the feeling that there is some interest in this very lightweight concretes. They can be an alternative for certain problems. And presently, we are doing we are making a project with Barco Leibinger in Berlin for well, it's not a high-rise building, but a high building. For German standards, it's already high-rise, made of such infra-lightweight precast elements. So perhaps we are lucky, perhaps it gets built. My last example, the last research example, is carbon fiber. Lightweight structures need high strength materials with little weight, and carbon fiber can be 10 times as strong as normal steel and weighs only 20%. So it's a wonderful material for lightweight structures. The big one is a hair. This is a human hair, and this is the carbon fiber, just to give you an idea. So you need many of those to really build something, and technology has advanced so far that yes, we can build a lot with it. And I don't think that it's enough just to glue carbon fiber on old concrete structure. It's a waste for this wonderful material. So we are trying to work with all carbon fiber structures. So this is our first little spokes wheel. But anyways, this just shows you the carbon fiber. See how slender it is here? It's very slender bands, highly tensioned. So strong you could hang a car on that, you know, but it's few hundred grams of material. Well, I have to admit the connections are still made of aluminum, but these bands, our PhD students make them themselves. You can do this yourself, and you see how slender this can become highly tensioned elements. So perhaps stadium roofs, steel cables can be replaced by carbon very soon. I believe that this will be the case. This is the pink area here, the pink surface. That would be the cost of a steel roof, steel cables. We know a bit what these cables cost, and we have compared them to different carbon fiber cables. There's very different carbon fiber materials. You see down here the modulus of elasticity from 120,000 Newton per square millimeter to 300,000, and here the stiffness, the strength from 2,000 Newton per square millimeter to 3,500. There's very different carbon fiber materials, and you see that they're extremely expensive ones that you use for satellites, but the ones with low stiffness, with low modulus of elasticity, they're in the range of 100%. That's the message here. You can build such a cable roof at approximately the same cost already as a steel roof. And well, now you have to see those again. These are two brave men sitting at the inner ring of a ring cable roof. So this is the inner ring, and this is a radial cable, and they're just connecting the radial cable to a very heavy cast steel element. You see the pin. This is the pin on their lap here, so they should not lose it. They have to connect the two elements then. And perhaps in the future we can replace these heavy cables with small carbon fiber cables. That's the idea of this little picture. But that would be too simple. That would just be replace a steel cable with a carbon fiber cable. Maya has understood the potential of concrete, and perhaps we haven't really understood the potential of carbon fibers yet. But perhaps in the future there will be no cables anymore. It will be a textile roof that is strengthened where you have more tension, and then these carbon fiber elements can be used in a completely different way. We have years ago already played with carbon fibers for stress ribbon bridges. This is a typical stress ribbon bridge, the way we designed them in our office, a steel band. This is high strength steel, S460, two bands crossing a saddle here. And the bending is the problem there. The saddle causes a lot of bending in a 3 centimeter steel plate. But if you have 0.1 millimeter carbon bands, then you can wrap them around such pins without causing too much bending. So that was the idea. We have used 0.1 millimeter carbon bands. We have wrapped them around 10 times, so the thickness of the band in the end is 1 millimeter. The highly tensioned band, this is in our lab again. And then we found out that it's very lively. That's the price you pay for very lightweight structures. It's a 13-meter span bridge with 1 millimeter of structural height, so you walk on it and it moves a lot. And this is why we have we have extended the project. So to say, we have equipped the bridge with accelerometers, so it's full of sensors. These sensors can find out if it's the first or second eigenmode, or if it's torsion. There's a processor here, and this processor then helps to inflate artificial muscles, tubes, within milliseconds, basically in real time. So whenever there's a movement, there will be muscles that counteract. They're inserted in the railing. You see these muscles here? They're nothing but tubes from Festo. So this is the uninflated tube, and if you inflate it, it gets bigger and it contracts, and the forces are up to, what was it, 6,000 newtons. And when they counteract, they reduce the accelerations, they reduce the movement a lot, the damping is tremendous. Anyway, this is our lab. A glass roof from 1912, so Behrens did a lot of good for the workers. You know, they could work with natural light 100 years ago. This is the stress ribbon bridge. You see the millimeter of carbon fiber and the concrete slabs on top, the pins, the muscles here. And now one of my assistants goes onto the bridge. You'll see two bridges. One is where the dampers are active, and the other one is the dampers are not active. So he's exciting now the first eigenmode. here they are slack and here they are active. And you see how the damping has changed dramatically. And now he will do the same thing again in the quarter point, so he's moving a bit faster and activating the second eigenmode, because we got this is how the muscle works. Little machines. It was a PhD thesis, and it was a lot of work and a lot of fun to do that. And the bridge can carry the load. This is the proof. Well, and perhaps in the future we can then build bridges like that, roofs like that with carbon fibers also, because this would be a wonderful project, because it's highly tensioned cables and cable nets. Anyway, this is my last slide and my thoughts on the Gesamtkunstwerk. My views got shaped by the achievement of other engineers, and I wanted to first pay tribute to these personalities, and my father is certainly one of them. I try to describe the principles of good design, the way I see them, and how we try to practice them in our office. Such principles need to form an important part of engineering education, and they can fuel scientific research to face the coming challenges in our profession. I think that well-educated engineers who know their history and who can combine sound theoretical and scientific knowledge with creativity are able to fuse the arts of construction into a Gesamtkunstwerk. Vielen Dank. Thank you very much.